All right, well, hopefully, before you started this video, you had a moment to reflect on the way you visualize an electron or the way you visualize light when I say those words. And this is really as a way to check in with what our current understanding is of these two things. And then we'll reflect at the end of this and hopefully we'll have changed that. Or maybe you're already there and have a really crystal clear picture of what these things are. Um, so for an electron, since we're not in a class sharing this, I'll share what I typically see from students. It's usually some sort of sphere, maybe with a negative charge added to it. Um, and this is how we've discussed an electron to date. It's this little tiny particle that has very small mass, but has a -1 charge. Um, I've always thought of mine. Here's how I tend to draw mine. They always have a little tail. They've always got some sort of smile. They usually have on some sort of hat as well for some reason. And sometimes they're smoking cigars. I don't know why. I think it's so that way the trail of smoke can wisp behind them as they move really quickly through the universe. Um, but here's a great start. Light, oftentimes I get students drawing light bulbs. That's a great everyday example of what light is to us. Or I get waves because light actually is electromagnetic radiation. It's a wave that travels through space that we observe with our eyes. I've seen some students like to draw a prism of light coming in and then being diffracted into its different wavelength components. That's always fun too. So just kind of hold your picture of what these two things are, and we'll talk about the nature of electrons. We'll talk about the nature of light in this video, because that nature of how electrons and light behave ends up being this other foundational piece to our picture of what an atom looks like. And so it's really key to the quantum model of an atom. So with that, let's start with the dual nature of light. And we'll work with light first. Then we'll look at the electron, and then we'll kind of bring these two together. So thinking about light. So light as actually just electromagnetic radiation. It's a form of it. Electromagnetic radiation will take a broad spectrum of types of energy or radiation that behave as a wave. So light as a wave is composed of perpendicular oscillating waves. So perpendicular and oscillating. That perpendicular and oscillating means that they're 90 degrees apart from one another. And oscillating is that up, down, up, down, up, down that we think of when we learned about sine waves in math. Um, and we have these two waves that compose light because one is going to be the magnetic field of light, and the other will be the electric field component. Um, and together, these make up light. So this wave of light can travel through space if it is in a vacuum at, get this, the speed of light. Okay, sorry, that was just phrased a little odd. But the speed of light is 3 times 10 to the 8th meters per second. It's pretty fast. So looking at these wavelengths of light or electromagnetic radiation, we can we can measure them in two main components. Just looking at the wave written out on a piece of paper in 2 dimensions. One, we have the wavelength of the light, which is really the distance between two peaks in our oscillating wave, or it could be from two places where it crosses zero, where it makes a full, it traverses both down and up. The amplitude is another component of this. The amplitude is really that height between what we're thinking of as zero and the peak of the wave or the valley of the wave. It's the maximum or minimum height that it can achieve. And we think of this really as the intensity of the wave. Nodes are another important one. Oh, the node is where the wave crosses past zero on a XY axis. Um, the other way to think of it from a chemist perspective is where it changes sign from being positive to negative. So I've got a node here and here and here and here. And as a chemist, I think of this as being in the positive region and this being in the negative region. Each of these distances between our nodes should be a constant distance. And so if we look at our wavelength, it's really going to be essentially the distance between two nodes as well. We can relate these to one another through, well, sorry, we can measure wavelength in terms of centimeters or meters or nanometers. Um, and that's really just a measure of distance between those peaks. We also have a value called frequency that we use more than amplitude in chemistry, though amplitude's important in other areas. And it's really going to tell us the number of waves per second that pass a point in space. So if I imagine a point in space here, and this wave is traveling this way, it's how many of these waves, so one wave like that, or one wavelength, will pass by this point in a given amount of time, usually in seconds. So our units for these are usually hertz, and a hertz is a cycle per second. And we actually use then just units of inverse seconds, or 1 divided by seconds. And a cycle is referring to one wave or one wavelength. So we can relate frequency and wavelength to one another with the equation wavelength times frequency equals the speed of light. So that's wavelength times frequency equals the speed of light. And remember that speed of light was 3.0 times 10 to the 8th meters per second. So I could think of my wavelength component of this equation being in units of meters, because this is a measure of distance, and frequency, if it's in hertz, is 1 over seconds. And that's how we get those units of meters per seconds. What changes in wavelength and changes in amplitude would mean to us visually um, are really about color and brightness. So if we change our wavelength, we will change the color that we observe or the type of electromagnetic radiation we're looking at. So here we have a larger wavelength and we see a red color. If we make that wavelength smaller, which would increase its frequency too if it was traveling at the same rate, we would have a smaller wavelength and blue light. Now, if we increase or decrease the amplitude, what we're really doing is changing its brightness. So as amplitude decreases, the light becomes dimmer. And as amplitude increases, then we have a brighter light that to us visually. So within the electromagnetic spectrum, I think one of our favorite pieces is visible light. This is how we see our world. And these are the wavelengths of light that our eye can detect. So if I shine just white light, so I've got white light right here, through a prism, it'll diffract it such that it separates out each of the component wavelengths of light. And so I can see all the different wavelengths of light that make up white light. And that's going to be all light in the range of 400 to 700 nanometers for a wavelength. So these values right here at the top are wavelength. And instead of meters, these are nanometers. Looks like an M. It's really an N, nanometers. So they're small. They're really small. And out here at 700 nanometers, we have red, and out at 400 nanometers, we have blue. And so 400 nanometers is a smaller wavelength, and our 700 nanometers is a larger wavelength. So here's the entire electromagnetic spectrum. You can see that our visible light region is a very small component of it. Between 750 and 400 nanometers in wavelengths, and this is in a nanometer scale here, but when we're looking at this scale of all of electromagnetic radiation, we're really looking at wavelength in meters. And we have this corresponded also into frequency up here in hertz, which is 1 over a second. And if we look at these, we could see that as our wavelength decreases, we see an increase in our frequency, which makes sense. As that wavelength decreases, more cycles will pass per second past a given point of observation. Now, our low wavelength, high frequency electromagnetic radiation is going to correspond to high energy. And our large wavelength, but small frequency is going to correspond to low energy wavelengths of electromagnetic radiation. And so down on the low energy end, we've got things like radio waves and microwaves and infrared. And then we hit our visible light spectrum. And as we get into higher energy, we have ultraviolet or X-rays or gamma rays. And gamma rays are kind of like cosmic rays. They're also sometimes emitted by decaying nuclei. And so here's some of the ways we use these. So our visible light is what we see. And the lower energy spectrum, we can use infrared light for thermal imaging of this adorable kitty cat. And on the higher energy spectrum, we have X-rays and gamma rays, which we can actually use for radiation therapy and harness that power to destroy specific cells. All right, so here is an important property of waves, and it's interference, and it's how waves interact with each other. And there's constructive interference. This is when waves interact so they add up to make a larger wave. We call it being in phase. And see, the peaks and the valleys perfectly match up into in-phase waves. And so they add together and they create this wave that has a larger amplitude, but the same frequency. Or the same wavelength is another way to think of that. So we call this constructive interference, where they add together. The other type of interference or way they interact is destructive interference. So this is when they are out of phase and they actually cancel each other out. And you'll notice that instead of both of the maximums being lined up, a maximum is lined up with a minimum on another wave, or a minimum with the maximum. And so when we sum these together, they actually cancel each other out, and we see no amplitude, and we lose our wavelength. And so it's as if it turns the light out when we have destructive interference. And so depending on how these waves line up as they interact with one another, we'll see them either get brighter or we'll see them disappear, become so dim we can't see them. So a property of this is, or a property we track in light, is diffraction. It's what happens when light passes through, a small hole. The idea of waves that we are used to seeing on the beach can sometimes be helpful because you can actually see it. If there's a small break right here in a barrier for water, as the waves crash up against it, they'll come out and they'll make this kind of ring pattern that we call a diffracted wave as it comes out. And so light will do the same thing. It comes in as a wave. If it hits a small hole in a barrier, then it will diffract that light out in this circular wave pattern, where it's a diffracted wave. Now, if we took a beam of particles instead and passed it through a small hole like this, we wouldn't see that same diffraction pattern. We wouldn't see it spread out like this. We would just see some of these stopped by the barrier and some of them continue through on the same path they were on. And so that means when we actually, if we put something here to catch this light or catch these particles, we would see particles appear just in one spot, and we would see the wave appear over a large region. So combining diffraction and interference, if we shine light as a wave at a barrier that has two slits this time rather than one, we'll diffract each of the wave will diffract at each of these slits. And as it diffracts, it'll start to, if you kind of continue this out, it'll start to overlap. And those points of overlapping will have both constructive interference, where they overlap in the same phase and they get brighter, or it will destructively interfere, and there'll be places where the waves overlap out of phase and they'll become dimmer or completely or gone. It'll disappear. There won't be a wavelength anymore. And so when you have two slits and you shine light through it, those diffracted waves create what we call a diffraction pattern, where we see bright light interspersed with blackness. And this corresponds to the destructive interference, where it's black, and the constructive interference, where it's light. And so that constructive interference is right here, showing that these waves add up to one another. And these areas of destructive interference are where the waves are out of phase and they cancel each other out. And so this is this lovely way of looking at light. You can shine it through two slits and see this pattern, and it's a lovely predictable thing that confirms something is light. So I'm going to have this link in a following video, and it's showing light behaving as a wave, and it's showing that diffraction pattern through two slits and having a laser shine through it. So you can see what that diffraction pattern actually looks like. You want to not click my link, here's the link for you as well. So we'll follow that video with discussing the second half of light's behavior, which is behaving as a particle rather than as a wave.